Welcome back. Last episode we built the three-dimensional stage, axes oriented by the right-hand rule, the distance formula, surfaces, level curves. Today we install the algebra that lets us actually move around on that stage. The protagonist is the vector. A vector is an arrow with a length and a direction. Equivalently, and this is the key duality, a vector is an ordered tuple of real numbers. Two perspectives on the same object, geometric and algebraic. Switching between them on demand is most of what doing multivariable calculus feels like. We will define addition and scalar multiplication. We will define the magnitude. Then we hit the two products that make vector calculus possible. The dot product multiplies two vectors into a number that encodes the angle between them. The cross product, defined only in three-dimensional space, multiplies two vectors into a third vector, perpendicular to both, whose length is the area of the parallelogram they span. We close with the right-hand rule, a few applications, and a short history. The story of how Hamilton's quaternions became the vectors we know today. A vector has two faces, and you need both. Algebraically, a vector in n-dimensional space is just an ordered list of n real numbers. We write it in angle brackets, v equals the list v1, v2, v3, numbers in, numbers out. That's the perspective you use when you want to compute. Geometrically, a vector is an arrow. It has a length, which we call the magnitude, and a direction in space. That's the perspective you use when you want to understand what a computation means. There are two conventions for where to draw the arrow. The first is the position vector, tail at the origin, tip at the point v1, v2, v3. In this convention, vectors are just points in disguise. The second convention is the free vector. The tail can sit anywhere. Two arrows that are parallel translates of each other. Same length, same direction, different starting points, represent the same vector. The free vector is more honest about what a vector is, a displacement, not a point. We use angle brackets for components, parentheses for points. So the list 1, 2, 3 in angle brackets is a vector, and 1, 2, 3 in parentheses is a point. They have the same numbers, but they mean different things. Vectors get bold or arrows over them, in handwriting, always the arrow. Two operations are built in. The first is addition. Algebraically, you just add componentwise. The first component of the sum is the sum of the first components, and so on. Geometrically, vector addition is tip to tail. Draw u as an arrow. Now place the tail of v at the tip of u. The arrow that runs from the tail of u to the new tip of v is u plus v. Equivalently, the parallelogram law, if you place u and v with a common tail, the diagonal of the parallelogram they span is the sum. The second operation is scalar multiplication, a real number times a vector. Algebraically, multiply every component by the scalar. Geometrically, scaling by c stretches the arrow by a factor of the absolute value of ci, and reverses its direction if c is negative. So 2v is v twice as long, same direction. Negative 1 times v is v with the arrow flipped around. These two operations satisfy all the familiar laws. Addition is commutative and associative. Scalar multiplication distributes over vector addition, and the zero vector is the additive identity. N-dimensional space equipped with these operations is the prototype of an abstract vector space, but we won't need that level of abstraction today. Just the arithmetic. The magnitude of a vector is its length. For a position vector, it is the distance from the origin to the tip, which by the 3D distance formula, which we derived last episode, is the square root of the sum of squared components. The magnitude of v equals the square root of v1 squared plus v2 squared plus v3 squared. In n dimensions, it's the same Pythagorean expression with n squared terms. A couple of warm-up examples. The vector 1, 2, in angle brackets, 3 and 4, in the plane has magnitude the square root of 9 plus 16, which is 5. The classic 3, 4, 5 right triangle. The vector 1, 2, 2 in space has magnitude the square root of 1 plus 4 plus 4, which is 3. The three standard basis vectors I hat, j hat, k hat, which are 1, 0, 0, then 0, 1, 0, then 0, 0, 1, each have magnitude 1 and point along the positive x, y, and z axes respectively. Any vector v in three-dimensional space decomposes as v1 I hat plus v2 j hat plus v3 k hat. The two notations are interchangeable. To turn any non-zero vector into a unit vector in the same direction, justified by its magnitude, v hat equals v over the magnitude of v. This is called normalization. Unit vectors record direction with the length factored out. Now the first product. The dot product of two vectors, written u.vr, is a number, not a vector. Algebraically, you multiply corresponding components and add u01 v1 plus u2 v2 plus u3 v3 in n dimensions, n terms. Easy to compute. Here is the miracle. That algebraic expression has a geometric identity behind it. u.v equals the magnitude of u times the magnitude of v times cosine theta, where theta is the angle between u and v when they share a common tail. We take theta between 0 and pi so that the cosine carries all the directional information. This identity is the whole reason the dot product matters. On the left, an algebraic sum of products of components, coordinate dependent, easy to compute. On the right, a coordinate-free geometric expression involving lengths and an angle. Equating them gives the formula that solves an enormous fraction of multivariable geometry problems. Cosine theta equals u dot v over the magnitude of u times the magnitude of v. Type 2 vectors in component form into the right-hand side, and out pops the cosine of the angle between them. A few quick algebraic properties. The dot product is commutative, u dot v equals v dot u. It is bilinear, linear in each slot separately, and crucially, v dot v equals b1 squared plus b2 squared plus b3 squared, which is the magnitude of v squared. The magnitude squared is the vector dotted with itself, one bonus inequality. Since the absolute value of cosine theta is less than or equal to 1, the identity u dot v equals the magnitude of u times the magnitude of v times cosine theta implies that the absolute value of u dot v is less than or equal to the magnitude of v. That's the Cauchy-Schwarz inequality, and it will return when we study limits and derivatives in n-dimensional space. Two consequences of the dot product identity are pure gold. First, orthogonality. The cosine of pi over 2 is 0. So for non-zero u and v, the dot product is 0 exactly when u and v are perpendicular. We just computed I hat dot j hat equals 1 times 0 plus 0 times 1 plus 0 times 0, which is 0, and indeed the x-axis is perpendicular to the y-axis. The dot product is a perpendicularity detector that takes only a multiplication and an addition to evaluate. Geometry from arithmetic. Second, projection. Imagine shining a light perpendicular to v onto the line spanned by v. The shadow of u on that line is a vector pointing along v whose length is the component of u in the v direction. This is the projection of u onto v, denoted proj sub v of u. To derive the formula, demand that the projection of u onto v equals lambda times v for some scalar lambda, and that the residue u minus lambda v be perpendicular to v. The perpendicularity condition, u minus lambda v dotted with v equals 0 timed expanded with bilinearity, gives u dot v minus lambda times the magnitude of v squared equals 0, hence lambda equals u dot v over the magnitude of v squared. Putting it back, the projection of u onto v equals u dot v over the magnitude of v squared times v, a clean coordinate-free formula. If you first normalize v to v hat, the formula simplifies to u dot v hat times v hat with the scalar coefficient u dot v hat called the component of u along v. Projection will return in episodes on planes, on linearization, and on the gradient. Here is the geometry on one canvas. Two vectors, u and v, share a common tail at the origin. The red arc marks the angle theta between them. The light blue parallelogram completes itself by translating u along v and v along u. The dashed sides are those translated copies. Two quantities are encoded in this picture. The dot product, u dot v, controls the cosine of theta. The red dashed perpendicular drop from the tip of u onto the line through v gives the projection of u onto v, the shadow of u along v. Its length is the magnitude of u times cosine theta. And the parallelogram, its area is base times height, which works out to the magnitude of v times the magnitude of u times sine theta. That is, the magnitude of u times the magnitude of v times sine theta. That number is exactly the length of the cross product, which we are about to define. So the parallelogram serves two products at once. Its base projection reads off the dot product, its area reads off the cross product magnitude. Geometry compressing two algebraic operations. Now the second, stranger product. The cross product of two vectors in three-dimensional space is itself a vector, u cross v, with two defining properties. First, u cross v is perpendicular to both u and v. Out of two vectors comes a third, sticking straight out of their common plane. Which of the two perpendicular directions? The one picked by the right-hand rule in a moment. Second, the length is the magnitude of u cross v equals the magnitude of u times the magnitude of v times sine theta. Notice the sign, not cosine. If u and v are parallel, theta is 0 and the cross product is 0. If perpendicular, it has maximum length, the magnitude of u times the magnitude of v. To compute, write the formal determinant with I hat, j hat, k hat on top, u in row 2, v in row 3. Expand along the top with the checkerboard signs. First component u2v3 minus u3v2. Then minus u1v3 minus u3v1 for the j hat slot. Then plus u1v2 minus u2v1 for the k hat slot. That middle minus sign is the most forgotten part of the formula. One striking fact, a product that takes two vectors to a perpendicular third exists in exactly 3 dimensions. Not in 2-dimensional space, 4-dimensional space, or 100-dimensional space. The cross product is a gift of 3-dimensional geometry. There's also one in 7 dimensions, but it lacks most properties we care about. 3 is its home. Which of the two perpendicular directions does u cross v point? The right-hand rule picks the choice. Take your right hand, point your fingers along u, curl them toward v through the angle less than pi. Your thumb now points along u cross v, same right-handedness that orients our 3D coordinate system. One immediate consequence: swap the order to v cross u and your fingers curl the other way so the thumb flips. The cross product is anti-commutative, v cross u equals negative u cross v. Order matters. The magnitude has a clean geometric meaning. The magnitude of u times the magnitude of v times sine theta is the area of the parallelogram spanned by u and v. Take the magnitude of v as the base. The perpendicular height from the tip of u is the magnitude of u times sine theta. Area equals base times height. So the cross product produces a vector, whose length encodes an area and whose direction encodes the orientation of that parallelogram. Basis identities to memorize. I hat cross j hat equals k hat, j hat cross k hat equals I hat, k hat cross I hat equals j hat. Cyclic. Reverse the order, pick up a minus sign. Useful properties. The cross product is bilinear. Crossing a vector with itself gives 0. Dotting the cross product back into one of its inputs always gives 0. The perpendicularity property restated. And it is not associative. In general u cross, the quantity v cross w is not equal to the quantity u cross v crossed with w. The correct identity, BAC cab, will meet when we need it. Here is the right-hand rule made visible. Two vectors, u in blue and v in orange, lie in the xy plane, sharing a tail at the origin. The light blue parallelogram is the region they span. The orange curling arrow swings from u counterclockwise toward VW. That's the path your fingers trace when you orient your right hand for the rule. The red vector going straight up the z-axis is the cross product u cross v. It points along the direction your thumb sticks when your fingers do that curl. The little right angle marks at the base confirm that the red arrow is perpendicular to the entire blue parallelogram, and so to both u and v individually. If you reverse the order, computing v cross u, your fingers would curl the other way around, the thumb would point down, and the resulting cross product would be the same vector with its sign flipped. That sign flip on swap is the geometric content of anti-commutativity, and the length of the red arrow equals the area of the light blue parallelogram. Cross product magnitude is area. First worked example. Let u be the vector 1, 2, 3, and v be the vector 4, 5, 6. Find the angle between them. Step 1, the dot product. Multiply corresponding components and add. 1 times 4 is 4, 2 times 5 is 10, 3 times 6 is 18, 4 plus 10 plus 18 is 32, so u dot v equals 32. Step 2, the magnitudes. The magnitude of u is the square root of 1 plus 4 plus 9, which is the square root of 14. The magnitude of v is the square root of 16 plus 25 plus 36, which is the square root of 77. Step 3. The cosine of the angle is the dot product over the product of the magnitudes, that is 32 over the square root of 14 times 77, which is the square root of 1078. Numerically, about 0.9746. The cosine is very close to 1, so the angle is small. Arc cosine of 0.9746 is about 0.226 radians, which is roughly 13 degrees. That makes intuitive sense. The vector 4, 5, 6 is not too far from being a positive scalar multiple of the vector 1, 2, 3. If they had been exact multiples, the dot product identity would give cosine theta equals 1 and theta equals 0. They are close to that degenerate case, so the angle is small. The dot product just gave us, in 3 multiplications and 2 additions, a number whose interpretation is the cosine of an angle in 3-dimensional space. That is the magic of the geometric identity. Second worked example, the cross product of the same two vectors. Set up the formal determinant with I hat, j hat, k hat on the top row, u equals the vector 1, 2, 3 on the second row, and v equals the vector 4, 5, 6 on the third. Expand along the top row with the checkerboard signs plus, minus, plus. The I hat component, 2 times 6 minus 3 times 5, which is 12 minus 15, equals negative 3. The j hat component, with its minus sign in front, minus the quantity 1 times 6 minus 3 times 4, which is 6 minus 12, equals negative 6. Negating the negative gives plus 6. The k hat component, 1 times 5 minus 2 times 4, which is 5 minus 8, equals negative 3. Assembling, u cross v equals negative 3 I hat plus 6 j hat minus 3 k hat, which is the vector negative 3, 6, negative 3. 2 quick sanity checks that you should do every time you compute a cross product. First, the result must be perpendicular to both inputs. Dot u with u cross v, 1 times negative 3 plus 2 times 6 plus 3 times negative 3 equals negative 3 plus 12 minus 9 equals 0. Good. Now v with u cross v, 4 times negative 3 plus 5 times 6 plus 6 times negative 3 equals negative 12 plus 30 minus 18 equals 0. Also good. Both perpendicularity checks passed, so we didn't blow the determinant signs. Second, the Lagrange identity, the magnitude of u cross v squared plus u dot v squared equals the magnitude of u squared times the magnitude of v squared. Here, the magnitude of u cross v squared is 9 plus 36 plus 9, which is 54, and the magnitude of u squared times the magnitude of v squared minus u dot v squared is 1078 minus 1024, which is 54. Match. Algebra consistent with sine squared plus cosine squared equals 1. Third worked example, a sanity check classic. Find a vector perpendicular to both the vector 1, 0, 0 and the vector 0, 1, 0. These are I hat and j hat, the first two standard basis vectors. We know the answer should be along the z-axis. Let's see if the cross product agrees. Determinant, top row I hat, j hat, k hat, second row 1, 0, 0, third row 0, 1, 0. Expand. The I hat coefficient is 0 times 0 minus 0 times 1, which is 0. The j hat coefficient, with the minus, is negative, the quantity 1 times 0 minus 0 times 0, which is 0. The k hat coefficient is 1 times 1 minus 0 times 0, which is 1. So I hat cross j hat equals k hat, which is the vector 0, 0, 1. Pure positive z direction, magnitude 1. And the right-hand rule confirms, point your fingers along positive x, curl them toward positive y, your thumb points along positive z. This single cross product identity is the right-handed orientation convention of our coordinate system encoded algebraically. The cycle continues, j hat cross, k hat equals I hat, and k hat cross I hat equals j hat. And reversing the order in any of these flips the sign. These 6 identities are the multiplication table of the basis, and once you know them, you can derive the determinant formula by bilinearity in under a minute. Why do these products matter outside a calculus class? Because they are the machinery of classical physics. Work. When a constant force, vector F, pushes an object through a displacement, vector d, the work done is W equals vector F dot vector d. The dot product answers how much of the force is doing useful work along the direction of motion. The perpendicular component contributes 0, which is why carrying a suitcase horizontally counts as no work even though it tires your arms. In data science, two feature vectors are compared by cosine similarity, which is exactly the cosine of the angle between them. Documents, images, embeddings, all measured by a dot product. Now the cross product. Torque is vector tau equals vector r cross vector f, the rotational effect of a force at a lever arm. Angular momentum is vector L equals vector r cross vector p. The Lorentz magnetic force on a moving charge is vector F equals q times vector v cross vector b. The cross product is everywhere. Geometrically, the cross product of two vectors in a plane gives a vector normal to that plane, which we'll use next episode to write equations of planes. And the magnitude is the area of the parallelogram, so half is the area of the triangle. Two formulas at once. A short history. In 1843, William Rowan Hamilton invented quaternions, a four-dimensional algebra whose 3 imaginary parts multiply exactly like our I hat, j hat, k hat, same cyclic identities, same sign on reversal. For 40 years, quaternions were the standard tool for 3D physics. In the 1880s, Josiah Willard Gibbs at Yale and Oliver Heaviside in England independently extracted the vector pieces, dot product, cross product, vector calculus, from the quaternion framework. Their notation is what every engineering and physics student learns today. Quaternions themselves have returned in computer graphics as the preferred way to encode 3D rotations. Recap. A vector in n-dimensional space is an ordered tuple, or an arrow with magnitude and direction. Addition and scalar multiplication are component-wise algebraically and tip-to-tail or stretching geometrically. Magnitude is Pythagoras. The dot product u dot v equals u1 v1 plus u2 v2 plus u3 v3 outputs a scalar and equals the magnitude of u times the magnitude of v times cosine theta. It detects perpendicularity, u dot v equals 0 if and only if u is perpendicular to v, and computes angles. Projection, the projection of u onto v equals u dot v over the magnitude of v squared times v. The cross product, defined only in 3-dimensional space, is the determinant with I hat, j hat, k hat on top, u and v below. Output is a vector perpendicular to both, with magnitude, the magnitude of u times the magnitude of v times sine theta, equals the area of their parallelogram. Right-hand rule fixes orientation, anti-commutative. 3 examples. The vector 1, 2, 3 dot the vector 4, 5, 6 equals 32, angle about 13 degrees. The vector 1, 2, 3 cross the vector 4, 5, 6 equals the vector -3, 6, -3, perpendicular to both inputs. I hat cross j hat equals k hat, the right-handed orientation encoded as a single identity. Applications, work, torque, normals to planes, parallelogram, and triangle areas. History, Hamilton's quaternions, 1843, Gibbs and Heaviside extracted modern vector calculus in the 1880s. Next episode, the limit gets reimagined in n-dimensional space, where approaching from infinitely many directions changes everything. That's the algebra of arrows. Vectors are ordered tuples, and they are arrows. They add componentwise and tip to tail. They have magnitudes via Pythagoras. They combine into a scalar via the dot product that knows the angle, and into a vector via the cross product that knows the area and orientation of the parallelogram they span. Two products, two faces of 3D geometry. If this helped, like, subscribe, drop a comment. As a small experiment, pick any two non-parallel vectors, compute u cross v, then dot it back into u and into v, 0 every time, regardless of inputs. A satisfying check that the determinant formula really does what we claimed. Next episode, we leave algebra and return to analysis. We redefine the limit for functions of multiple variables. A one-variable function has only two sides to come at a point from. A two-variable function has infinitely many. The new subtleties are real, and they make multivariable continuity its own subject. See you there. Today we made arrows algebraic. A vector in R to the n is an ordered tuple of real numbers. Geometrically an arrow with magnitude and direction. Algebraically a list of components. Addition is pairwise on components and tip to tail geometrically. Scalar multiplication is pairwise stretching. The magnitude v equals the square root of v1 squared plus v2 squared plus v3 squared is the Pythagorean length. The dot product, u dot v equals u1 v1 plus u2 v2 plus u3 v3 equals uv cosine theta. So it reads off angles, detects perpendicularity via u dot v equals 0, and computes projections, proj v of u equals u dot v. The cross product u cross v, defined in R cubed via the determinant of I, j, k over u over v, produces a vector perpendicular to both with length uv sine theta, the area of the parallelogram they span. Orientation comes from the right-hand rule. Worked examples, the vector 1, 2, 3 dot the vector 4, 5, 6 equals 32, the vector 1, 2, 3 cross the vector 4, 5, 6 equals the vector minus 3, 6, 3 hat emath cross hat jmath equals k. Applications, work w equals f dot d, torque tau equals r cross f, normal to a plane. Historically, Hamilton invented quaternions in 1843, and Gibbs and Heaviside extracted the vector calculus we still use today. Next episode, the central analytic concept of calculus. The limit gets generalized to multiple variables, where approaching from every direction breaks our one-variable intuitions. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.